Astronomers from the International Centre for Radio Astronomy Research have made a discovery of a new cosmic phenomenon, ASKAP J1832-0911. This object emits pulses of radio waves and X-rays for 2 minutes every 44 minutes, marking the first detection of long-period transients in X-rays. Associate Professor Clancy James is beaming in to take us on a deep dive. Professor, thanks for your time. What is this object that's written the first entry, pretty much the first entry in the Long Period Transient book?
Well, thank you, Matt. And what it is really the key question here. So as you described, it's something that emits for 2 minutes every 44 minutes, and we see it in radio and X-rays. But what it fundamentally is, what the nature of this object is, we're not quite sure. We have a couple of key theories, but I think it's going to take a few years for us to pin down exactly what's going on.
The discovery is the convergence of a bit of luck, with ASKAP viewing the area of sky broadly and Chandra also in the neighbourhood with its tighter field of view.
Absolutely. I mean, there's actually two pieces of luck that come in here. First of all, ASKAP caught the source when it was extremely bright. This is not the first long period transient to be discovered. There's been other sources with periods between about 8 minutes and 6 hours that have been seen, but this has been by far the brightest. Now, we know that some of these sources have been active for 30 years or more, and others seem to come or go every couple of months. And so we were, first of all, really lucky to be able to observe this one when it was incredibly bright. It was one of the top few dozen radio sources in the entire sky when we first observed it. It was booming through. And then the next piece of luck was that it turned out that when it was really bright in radio, that the Chandra X-ray telescope was observing that piece of sky for a completely different reason. And so we were able to get hold of that data and see the X-rays at the same time that the radio was at its brightest. And that seems to be when the X-rays were at their brightest as well.
And this is the best part I love about science and researching the night sky. Around the world, there are so many telescopes and observations and observatories doing their thing in the sky that there is this collaborative community that, hey, were you guys checking this out? Yeah, indeed we were. Let's share the data and have a look at it.
Yeah, it's really fantastic. If you look at what was taken to put together our current understanding of this object, right? We had the ASKAP radio telescope here in Western Australia, but we also used radio telescopes in South Africa, in the USA, in India, and others in Australia to follow up the source, to keep monitoring it, to localize the exact position of it with higher precision. We used infrared telescopes in space to be able to search for stars that might be associated with this object, and we haven't found any stars associated with it. And of course, X-ray telescopes. And so it's been a really huge worldwide effort.
Now, ASKAP J1832-0911 could either be a magnetar or a binary system. I know you have to keep an open mind as a scientist, but what do you think it is?
This is a terrible question. I would like to think it's a magnetar. My own personal pet theory is that it's a very old magnetar. So it's not behaving like the standard magnetars that we know, right? The fact that it's periodic is relatively unusual for a magnetar. When we observe magnetars, they're typically found via their massive bursts of X-ray and gamma ray emission when they undergo a flare. It's a little bit like a solar flare. The sun will undergo a flare because of changing magnetic fields suddenly release their energy, and that occurs sporadically and suddenly and are very bright. Well, magnetars do something similar, but on hugely grander times, factors of energy, right? They could be hundreds of thousands of times brighter. I probably need to do the calculation of that. It's probably billions of times brighter. But these massive outpourings of energy. In this case, this is actually pretty dim. We only see the X-rays when it's at its very brightest. We've searched for X-rays at other times, both before and after this initial discovery, and they're not there. So if it is a magnetar, it's not a very active one. And this tends to suggest it's probably a very old object.
It's all very early days, but let's dive deep into these long period transients. Now, obviously that long period, it's kind of in the name, but can you break it down? What are long period transients?
Well, like typical astronomers, we name things in a fairly descriptive manner, right? So they have a period, first of all. They're objects that regularly will emit a pulse for some amount of time, then turn off, then turn on again. So classically, the most periodic objects we know are pulsars, right, which emit bursts of radio waves regularly from about once a millisecond to once every 10 seconds or so, maybe once a minute. And they're extremely regular objects. They're some of the best clocks in the universe, and we use them to perform timing experiments to test general relativity. But when people have been trying to work out how pulsars emit their radio emission, we have various theories, and they all seem to predict that after a certain time, as pulsars slow down, that the radio emission will turn off. It's like the rotation is the battery that's powering the emission, and at some point that battery runs down, and then they're no longer able to emit. So for a long time, we really thought that pulsars you couldn't really exist with periods longer than about 10 seconds. And then we discovered a few with periods of maybe 40 seconds or a minute, but they were more the exceptions that proved the rule, right? Very rare objects that are sort of at the extremes of the population. And then all of a sudden, we start seeing periodic radio emission, which seems to be similar to pulsars. It happens fairly regularly now and again, but it's over a much longer period. So they're long period transients, and the transient just refers to something that turns on and off in the sky, something that's non-constant. So from an observational point of view, this is what long period transients are, and the discovery of them has really been kicked off in the last sort of 5 years. There was one hypothetical source that was put forward in about 2006 from memory, and that was really the first one discovered, but it was a once-off. People didn't put too much stock in it. They didn't really understand the source. It was a sort of once-off observation. But then they've really been characterized due to observations with the Murchison Wide Field Array and my colleague, Associate Professor Natasha Hurley-Walker, who's really kicked off the rediscovery of these. And now there's a order 10 of these objects that have been detected. So they've been seen to have a wide variety of behavior. Even though they're periodic, they're sort of semi-regular, they will turn on and off. They might be on for, say, 2 minutes every 44 minutes, or perhaps 10 minutes every 6 hours, this kind of range of numbers. They still show a wide variety of behavior in terms of how regular they are. So as I mentioned earlier, one of them's been on for 30 years relatively constantly. One of them was observed to turn on for a couple of months, go quiet, turn on for a couple of months again, and then completely disappear. So regardless of what the fundamental object is and how the standard emission is being produced, we still don't have a reasonable model to explain why they sometimes seem to be so constant and sometimes they're turning on, turning off, completely disappearing.
The one thing that I find really interesting for me is that it's not just a matter of finding these objects, but it's finding these objects and staring at them long enough to see what they're doing. In this case of this long period transient, every on for 2 minutes every 44 minutes. So it's not just a matter of looking at it once, it's kind of collating that over hours and days to work out that, yes, indeed, this is a pattern.
Yeah, in a way, you need two kinds of instruments for this sort of work. You need one instrument to find these sources, and that has to have a wide field of view. You need to look at as much of the sky for as long as possible, simply because you don't know when these things are going to turn up. It's not like galaxies, which are always there, right? A galaxy doesn't suddenly turn on or turn off in any given instant. These things, you might search a patch of the sky for months and there's nothing there. Then you go back to the same patch of the sky the next year and there's some new source. So you need something to monitor that. But then, of course, you need this series of telescopes to really follow up these initial observations and characterize these sources. And that's really an ongoing piece of work. And ideally, we would like to monitor the entire sky all the time for periods of 10 years. But at the moment, that's just not technically possible.
And another thing I've noticed too is that we talk about the night sky. We're observing the night sky, or we're looking at the sky. That's really an Earth term, isn't it? We're kind of just looking at what we can see in the universe. We're studying this universe and finding these things that are out there.
Yeah, radio telescopes, of course, work perfectly well in the daytime. You don't want to point them too near the sun because the sun's a pretty bright source of radio waves. And, well, once we did point the ASKAP radio telescope at the sun, and it's meant to have some coating that diffuses the light, but actually that wasn't working because of water in the dish, and we did melt part of the antenna. But, these things happen. But, most of the time we can observe perfectly well during the daylight. But of course, the key thing here is in the southern hemisphere, we look towards the center of the galaxy. So Sagittarius, A star, the black hole at the center of our galaxy, and most of the stellar density in our galaxy is in the southern hemisphere. And that's where we've been finding most of these objects. Whereas a lot of other transients are extragalactic, and we don't sit in any particular special place in the universe. But the best place to look for extragalactic objects is away from our galaxy, because then our galaxy is a whole bunch of stars and gas and dust that gets in the way of the rest of the universe.
What does this discovery mean for the future of LPT research?
Well, I think it means two things. One is it tells us a new observational strategy, right? It's really key to monitor these things for when they're really bright, and then to immediately try to follow up with X-rays then, right? One of the things we found with this is that we don't see the X-rays when it's merely normally bright. We need to wait for the highest outburst. And what this means is we have to wait and continually monitor these sources to find when they're brightest. And then immediately, and when I say immediately, within a week or two, make deep X-ray observations to see if they are actually emitting X-rays. I mean, previously, plenty of people have looked at LPTs, other LPTs in X-rays and seen nothing. But they didn't do that when they were at their brightest, and none of them have been as bright as this one. So I think, first of all, it means that observers will change their strategy. They'll be reinvigorated search for X-rays, but they won't just point at a random time. It'll really be timing is critical. So that's part one. Part two is it's a theoretical challenge as to what actually produces this radio emission. So it was starting to look like, before the observation of this object, that actually LPTs might all be white dwarfs in binaries with low mass stars. So this is where you have a relatively low mass star, dimmer than our sun typically, and a white dwarf, the dead stellar remnant of a stellar mass object. Now, our sun will one day become a white dwarf. And these objects have magnetic fields, and it's been due to the interaction of the magnetic fields between the white dwarf and the star it's orbiting that produces the radio emission. Maybe not too dissimilar to the way that the magnetic field of Io and Jupiter interact to produce radio bursts from Jupiter. So it's been confirmed that at least two of these long period transients are white dwarf binary systems like that. And that's really interesting. And so as soon as you have an unknown population, and then two of them seem to be white dwarfs and binaries, you start to think, well, maybe all of them are. Right? But then the question arises, how on earth do you get X-ray emission out of such a system, and in particular periodic X-ray emission? And that's something where we don't really have any good theories for how that occurs. So I think there's going to be a real theoretical challenge to see, can white dwarfs and binary systems produce periodic X-rays? And for that matter, can magnetars? Because we know that magnetars can easily produce X-rays, but to do so in a dim but regular way is quite unusual.
And I know you mentioned that, some of these observations in the past haven't turned to the X-ray spectrum while these emissions were at their brightest. But there is a foundation of information there, of data collected in the past that you could potentially look back on. So you're not necessarily just relying on future data, or is it because of that missing link in the X-rays that we need to be looking towards this in the future?
Well, it's yes and no. So first of all, X-ray telescopes and radio telescopes tend to try to save all their data. In fact, we were able to go back and look in radio data where radio telescopes had coincidentally pointed at the source in the sky, and also X-ray data, and determined that actually it wasn't on, and it must have turned on fairly recently. Right? On the other hand, X-ray telescopes tend not to be very wide field of view. Most X-ray telescopes observe a relatively narrow part of the sky, say a fraction of the full moon. And so even though they are recording all the data that they take, you don't really find that there's a good chance of them pointing at the same part of the sky. So you can't really rely on that sort of observational data. There are satellites that observe in gamma rays, in particular the Fermi Gamma Ray Telescope, that is very wide field of view. It observes more than maybe a tenth of the sky at once. And so that has an excellent catalogue where it's guaranteed to be observing any given source at some interesting time, except we've had a search for gamma rays from this, using the Fermi data, and weren't able to find any hint of gamma ray emission, which would have been fantastic if we had.
Now, the International Centre for Radio Astronomy Research has been leading the charge in this, having first detected it in 2022. What is ICRA, and I guess where is it going to take us next?
Well, this is one of the big questions. So it's not just been in long period transients, but really we have a lot of groups focusing at different kinds of transients in this research space. So I previously mentioned pulsars, which have been known for a better part of 50 years now, maybe better part of 60. That's before my time. And trying to link pulsars and neutron star physics to these long period transients is one of the connections that we're trying to make. On the other hand, since 2007, people have been observing fast radio bursts, which are also, rapid bursts of radio waves, but they're not periodic, and we see them across a large fraction of the known universe. We've seen some of them being incredibly bright, much brighter than these long period transients. And also apologies for the background noises. That's emails coming in. I'll see if I can get rid of that nonsense.
You're a very busy man. I appreciate your time.
Oh, it's probably all spam. Anyway, and so fast radio bursts are another cosmic mystery as to how we get this kind of emission. Now, that's not similar to long period transients. They're not periodic. It's far brighter. But nonetheless, we believe that this may well be neutron stars doing weird things. In fact, I think that one title of our research here could be Neutron Stars Do the Darndest Things, right? We see them pulsating regularly. We see them, if they have extremely strong magnetic fields, emitting massive magnetic bursts. We may be seeing them producing long period transients. They might be producing fast radio bursts. And I think trying to get all these research groups that began looking at different phenomena to really unite to properly understand the underlying physics is where we want to focus for the next 5 years.
Fantastic, Professor. Thanks for beaming into this edition of Talking Science. Looking forward to more LPT discoveries.
Thank you very much, Matt. Have a good day.
Daily science and space stories with an Aussie flair, plus a deep dive into the science or space headline of the week and the occasional science fiction podcast. Like, follow and subscribe for more. Membership available to help us do more. thetrek.zone/support. This is Trekzone's Talking Science.